Hello. All right, this is going to be your force lecture for your midterm review. So to begin, forces are varied. So there's a lot of different types of forces. So there's two major types of forces that we've talked about so far, and those are, if I could get my pen to work. Okay. There's contact forces, and contact forces are when you are in contact with something, so touching, or there are field forces. And field forces are things like gravity or magnetism, which we haven't talked about yet. So a contact force is anything touching. So for our purposes, that is a push or a pull. For field forces, that's always gravity. So why is this important? Basically, contact forces only happen if there's a direct interaction, whereas field forces happen all the time. That's the major distinction. And that's really all that you need to know specifically about those two things. So in other terms of forces, we have a couple different types of forces. So our first force that we're going to discuss is going to be a push or a pull. So that can be written as something like FP, right? And FP usually represents a push or a pull. And for our purposes, that force is usually a constant application. So a problem would say something like a 3 kilogram block is pushed by a force of 5 newtons. So that just tells you that during the time that this is moving, there will be a consistent force of 5 newtons applied to it. So that's force P, which is push or pull. We then have force of friction, which is sometimes written as Fk. And Fk just stands for force kinetic. And the force of friction is just basically how rough a surface is. So that's essentially what friction means, is that there is a certain type of roughness that's present on the surface. So force of friction is roughness. Okay? So there's force friction, force of push, force of the pull, and then we have force of gravity, which is always mass times gravity. So you have to be very careful that it is not just gravity. A lot of you have been just using G, which is just 10, and that is not correct. So you have to multiply this by the mass in order to get the actual value for force of gravity. We then also have Fn, which is force normal, and the normal force has a couple of different potential values. So the normal force is the force that's coming from the surface. Because normal means perpendicular, we usually call this the support force. So there are a couple of different options. When you have a support force, that support force is coming from wherever the surface is. So if we have a surface that's at an angle and a box is on it, where is this being supported? That support is coming from the surface this way, right? Which means that this normal force is acting at an angle. That's different from when your object is sitting like this. Now that surface is flat, so that means that your normal force is acting straight up. Well, pretty much straight. Straight up as much as it can. Now with that happening, this arrow becomes your normal force in both cases. Now what we also have on this is force of gravity. And force of gravity is always straight down, all the time. And by straight down, I mean absolutely straight down. So when you look at these two things, even though right now there's only two forces acting on it, and technically it's the same box, so they should be the same forces, they're not. In this particular situation, when we have the force of gravity and the normal force on an angle, what's going to happen is that this box is going to slide down. And it's going to slide down due to the fact that gravity and normal force are unbalanced. Right, so pay attention to that. We'll talk about that later. But your normal force always comes from the surface. So depending on wherever that surface is located and how it's oriented, that will tell you what direction this is supposed to point. Okay. Now for force in general, the general formula for force, if I could write, is F equals ma, where m is mass and a is acceleration. So force equals mass times acceleration. What does that actually mean? This just tells you that when a force is applied to an object, it will accelerate if those forces are unbalanced. All right? So acceleration, meters per second squared, mass is in kilograms. So when you calculate force, it is measured in newtons, which are N. And those are kilogram meters per second squared. Kilogram from the mass, and then meters per second squared from the acceleration. So that's the unit, and then that's the formula. Now there's a couple different formulas, potentially. So we have the force of friction, and this formula is always the same. That's coefficient of friction multiplied by the normal force. Now the normal force in this particular situation is what changes, and there isn't one equation for normal force. Because normal is just how much the surface is supporting the object. So there's force of friction, and that's equal to coefficient times normal force. We have F equals ma, and then usually force of gravity, I say usually, I mean all the time, force of gravity is mass times gravity. And we pretend that mass is in kilograms, not pretend it is, and we say that gravity is 10, even though it's actually 9.81. So really the force of gravity is just 10 multiplied by whatever your mass is. Okay, so those are our three major ones. And then, like I said, normal force is very dependent upon the situation at hand. These are types of forces. Now, free body diagrams is the next big important thing to pay attention to. So even though on the midterm you're not going to have to actually draw them, you may have to answer a question based on... What is a rectangle? You may have to answer a question based on whatever it is. So they'll ask a question that says this surface is blah blah blah. What's a free body diagram? So I'll draw two different ones here to illustrate different things. So this is going to be on a flat surface, and this is going to be on an inclined plane or a ramp. So those two things are the same. So flat surface or a ramp. Now every single object, unless it's floating in space, is going to have a force of gravity. And that force of gravity, as aforementioned, is always straight down. So there's your force of gravity. And force of gravity is just mass times gravity, so that's what we got going on. Now, there's a normal force, and as already mentioned, the normal force is pointing wherever the surface is. So this one is going to be sitting on a flat surface, so normal force is pointing up. This one is on a ramp, so normal force is acting at an angle perpendicular to the surface. Okay, so force normal is always perpendicular to the surface. Okay, so that's the basic situation. Now, if there was friction involved in this situation, it would be opposite the direction of motion. So in order for there to be motion, on the flat surface at least, we should have given it some type of velocity, or we should be constantly applying a force. So let's just go with that. We're going to have an applied force, which is force push, to the right, which means that our force of friction is going to be to the left. All right, now on the ramp, we're going to be rolling down the ramp, so that's going to mean that our force of friction is acting up the ramp. Now we don't necessarily have to have a push or a pull downward, even though there technically is one. And the reason why that is because gravity is what's causing it to roll down the ramp, which we've discussed. But gravity points straight down, so that can actually be broken up into components, which is everybody's favorite. Where this becomes your force of gravity in the y direction, and this one becomes your force of gravity in the x direction. Altogether equaling your total force of gravity. So these are the two different types of free body diagrams that you can expect. Now, what you're supposed to do when you draw these is make sure that your arrows are corresponding to the relative size. So that means that your normal force and your gravitational force on the flat surface, because of what we know about flat surfaces, they should be equal to each other. So what this means is that your net force in the x direction, or y direction, I'm sorry, is equal to 0. Okay, so if normal is equal to gravity, that means your net force in the y direction is 0, which means that your acceleration in the y direction is 0, which means that there is no change in velocity in the y direction. So that in turn means that there is no change in y position. All right, so if you have a net force of y, that either means that there's no change in velocity, so it's either constant, which could mean that your change in y position is 0, or it has a constant velocity. Now, since it's sitting on a flat surface for this particular situation, we know that it's going to be the no change in position option, but it could also be moving at a constant velocity. All right, now if your left to right forces in this diagram are unbalanced, so that would mean for unbalanced forces that your force of push or pull is greater than your force of friction. That means that you do have an F net in the x direction. So F net x does not equal 0, which means that acceleration in the x direction does not equal 0. So there is a change in velocity in the x that again is non-zero. So this one again is accelerating, which means that there is absolutely going to be a change in x position. All right, so if your forces are unbalanced, then that means that you will have a change in velocity, you will have an acceleration, and you will have a change in position. So for solving these, you have a couple choices. Now the best way to do this, and this is where everybody gets a little confused, you have the generic form for force, which says F equals ma. So that can be rewritten as F net equals mass times acceleration net. It's the same thing, but this just says that this is your total. You also know, or maybe you don't know, that F net, the word net means the sum of all the forces. So F net is all of the forces added together. So if we're talking about the x direction for the situation above, that means we have the force of the pull or push and we have force of friction. Those are only two side-to-side forces. So if these two are not balanced, when we actually rearrange the equation, we end up with a non-zero value for acceleration based on the following manipulation of this equation. So pull and friction are in opposite directions, so technically one of these should be negative, and that's usually dependent upon which makes the most sense. Usually friction we make negative, but on occasion it can be the pull or the push. So F net x is mass times acceleration in the x direction. So mass times acceleration in the x direction, and that's going to be equal to your pull force minus your force of friction. From what we know, force of friction is coefficient times force normal, so we can substitute that in. All right, and then as already discussed, the F net in the y direction for this is 0, so that means that the normal force and the force of gravity are equal to each other. So that means that this is the force of the pull minus the coefficient of friction multiplied by gravity. The reason for that, as already discussed, but I'll write it down, is that normal and gravity are equal on flat surfaces. So because of this, we can end up with this equation to calculate the net acceleration if we wanted to. Now, I have to make a note about the equal on flat surfaces. There are some situations in which the normal force and the gravitational force are not equivalent. So a situation where that arises would look like this. So if you have an object like that, all right, and it is being pushed down at an angle, or pulled up at an angle. Let's start with pulled up at an angle. So your force of the pull, well, this is driving me bananas. The force of your pull, like that, is at an angle, which means that there is a component horizontally, which is FPX, and then there is a component vertically, which is FPY. And you have an angle here. All right, then you have all your basic forces that we've already talked about. You have a force of gravity, which is pointing down. You're going to have a normal force, which is pointing up. And then you can have a force of friction pointing backwards, because this is on a flat surface. Okay, now when you do your F net relationships, so we have already said that F net in the x, if your object is not accelerating, equals 0. If it is accelerating, you have the fact that you would have all of your x forces together. So you have FPX, and then you have force of friction. Those are your x forces. And then you do the same thing for y. So F net y is going to be force normal, which is pointing up, plus FPY, which is also pointing up, minus force of gravity, which is pointing down. And if your object is not leaving the surface, which for the most part is what happens, that's equal to 0. So that means that your force of gravity is equal to the sum of your normal force and your force in the y direction for the pull. So what that officially means in terms of calculating friction, by doing this, your normal force doesn't equal gravity. It actually is going to equal the force of gravity minus the pull in the y direction. So a good way to think about this is if you ever have had to drag something across the floor and you're pulling up at an angle, you have a tendency to have it leave the ground. I don't know if you've ever done that, but that's usually what happens. And even if you don't, by pulling upward, you are decreasing the amount of contact that the object has with the surface. And by decreasing the contact with the surface, you are therefore decreasing the normal force. And because the formula for force of friction is coefficient times force normal, when the normal force goes down, the force of friction goes down. So based on this relationship, your force of friction is smaller than it would be if you were pulling totally horizontally. Now the opposite is true if we do essentially the same thing, but we're going to push down. So when we pull up, let's rewrite that. So pull up, force normal is equal to force of gravity minus the pull in the y direction. When we push down, force normal is equal to force of gravity plus the pull in the y direction. Alright, so diagram-wise, what that looks like, you have your rectangle, and then you're going to have your force of gravity. Sorry. Oh my goodness gracious. Alright, you got force of gravity pointing down. You've got your normal force pointing up. Normal force of gravity. You got your friction going backwards. And then you have your push force. Now when you have your push force, you have a couple of different ways to draw this. Most of the time when you draw a free body diagram, you want the arrows pointing away from the object in the direction that they're moving. So if we're pushing down, like sweeping or pushing a vacuum or a shopping cart or something, the force that we're exerting is usually along the handle pointing into the object. Now we don't like that because it's pointing in. So what we want to do is put that on the other side, like so, which is not pleasant to draw or look at, so just stick with me for a second. Alright, so in this case, your force of the push is acting down at an angle to the right. So you still have your FPX going to the right, like in the previous situation, and then you're going to have your FPY, but in order to complete this triangle, it's pointing downward. So when you sum up your forces in the y direction, you have going up force normal. You have going down FPY and force of gravity. So that means that the two going down have to counteract the one going up. So that's why when you're pushing down, your normal force is greater, and when you're pulling up, your normal force is less. And that's if you're pulling up at an angle. Okay, so that's how you go about doing your free body diagrams related to your forces. Okay, so other force information, if we look at an inclined plane problem, just to make sure that we have this taken care of. Do I have the shape? No, I do not. Okay, so an inclined plane is some sort of ramp. Right, you usually have an object placed on the ramp, so it could be a ball, could be a block. For our purposes, even if it is a ball, we solve it like it's a block for reasons that we will talk about next month, so just ignore it for right now. Alright, so let's do a sample problem that I'm just going to make up right now. So we have a ball with mass of 3 kilograms. And this ball is located on this ramp that is angled at 22 degrees. And that angle is located at the bottom. So we have a mass of 3 kilograms. It's located 22 degrees. For the first situation, the coefficient of friction does not exist. This is a frictionless surface, so the coefficient is 0. So what we want to know is a couple things. What is the net force? What's the acceleration? And we could do a couple things depending on the problem. If we know how high up it is, we could figure out how much time it takes to reach the bottom. Or, what I'm going to try to do is if the object starts at rest, so V initial is 0, what is V final? So these are the three things that we're going to figure out. F net, acceleration, and V final. Alright, so in order to figure this out, I am going to say that the length of this ramp is 1.5 meters. So when I say length of the ramp, I mean the face of the ramp like that. So the diagonal is your 1.5 meters. Alright, first thing you have to do, free body diagram all the time. There's no way around it. So, free body diagram is going to go over here. Alright, so there is your object, which is your ball. And then what do we have? Pointing straight down is force of gravity. Coming from the surface, perpendicular to the surface, is your normal force. And since this problem does not have any friction, we don't have a force of friction acting upward. So that means our free body diagram is done. So what we have to do in order to solve this problem is to identify our directions. So what's x and what's y? So for this, we have one thing pulling straight down, which is normally y, and then we have our normal force, which is acting at an angle. But when our object moves, it's going to move along the plane of the ramp, which is also going to be at an angle. So this is where you want to rotate your coordinate system. So what we're going to do is say that the normal force is the positive y direction. Normal force is positive y, which means that we're going to have to generate other directions based off of this. So we're going to end up with an FGY, which is going to be the negative y. And then we're going to have an FG in the x direction, which taking it down the ramp means that it's going to be a positive x. So usually when we pick direction, we want it to be whatever is supposed to happen or conventionally will happen. And when you're rolling down a ramp, the x direction would be down the actual ramp. So when we do our problem, we have to figure out first force of gravity, just because that's the best thing to do since we know enough information to do so. So force of gravity is equal to mass times gravity. Our mass is 3 kilograms and our gravity is 10. So 3 times 10 is 30 newtons. So that's our total force of gravity. So from here, we can then break up our x and y pieces. It's usually a best bet. Anytime you're given an angle, you want to figure that out. So how do we figure out our components? The angle of our triangle is down at the bottom right. So that means when we do our component triangle, and this is always true for ramps, your angle is at the top. So the 22 degrees is at the bottom of the full ramp, but it's at the top of our component triangle. And for that, we have our trig functions of cosine, sine, and tangent. Now most of the time we're not going to use tangent, so I'm not even going to bother writing it. But cosine of theta is equal to adjacent over hypotenuse. And the sine of theta is equal to the opposite over the hypotenuse. So with this information, we can figure out FGX and FGY. So when we write this down, force of gravity is your hypotenuse. FGY, based on where our angle is the adjacent side, and FGX is the opposite side. So when we set up for cosine first, we say that cosine of theta is equal to adjacent over hypotenuse, which means that the cosine of 22 degrees is equal to adjacent, which is FGY, over our hypotenuse of FG, which is 30. So 30 multiplied by the cosine of 22 is equal to FGY. So for that value, we are going to get a number of, calculator out, 27.82. And that's going to be our force of gravity in the y direction. And due to the fact that things that are in the same plane are usually equal to each other, according to what we have established, our object doesn't leave the face of the ramp. It's going to roll right down. And our net y has to be 0 because of that. So that means if F net y is 0, that the normal force is also Fgy. Because in the y direction, we have Fgy and force normal, and that's it. So in order to cancel out, those two things have to be equal. Right, so that's how we find Fgy. So then we're going to do the same thing with sine. And now, if you notice, what we're doing is looking for, in both cases, the thing that's on the top of the fraction. Because when we talk about sine, we are going to be doing opposite over hypotenuse. And we know the angle and we know the hypotenuse. So when we rewrite that, we can write it as 30 multiplied by the sine of 22 equals the opposite. Alright, so which gives us, which is the opposite, FGX. Alright, so 30 times the sine of 22 is 11.24. Alright, so that's FGX. Now we're talking about net force, which is one of the things that we're supposed to find. So since, like I said before, it does not leave the surface of the ramp, that means that F net y is 0. F net x is going to be the sum of all of the forces in the x direction. And in our diagram, or free body diagram, since there is no friction, F net x is the only x force we have, which is Fgx. So that means F net is 11.24. So for this particular problem, our object is going to experience a force of 11.24 newtons. Now, we want to find acceleration. And acceleration is calculated with the net force situation. So F net is equal to Fgx, but the general formula for force says that F net is equal to mass times acceleration. So we know that we're experiencing 11.24 newtons. We know that the mass of our object is 3, so our acceleration is going to be whatever 11.24 divided by 3 is, which is 3.75 meters per second squared. Okay, so that's the acceleration. So we have found our F net as instructed, and we have found our acceleration. So the final step is to figure out what the speed at the bottom is. So this is when you throw it back to kinematics. So in kinematics, we have a couple equations that include V final. One is V final equals V initial plus acceleration times time. The other is V final squared is equal to V initial squared plus 2a delta x. Now for these, you want to go through every time you do a problem and look at what formulas you have and what you have in terms of variables and what you're looking for, and see which one has the most pieces. So we are looking for V final. We know V initial, we know acceleration, but we don't know time. So then we look at our next thing. We're looking for V final. We know V initial. 2 is a constant. We just calculated acceleration and we have delta x in the problem. So that means in that equation we have 3 things that we know and only 1 thing that we don't, as opposed to the previous equation where we have 2 that we know and then 2 that we don't. So we're going to use the V final squared equation because that has all of our variables that we need and all the ones that we want. So when we plug in with that, V final squared is what we're looking for. So that means that V final is going to be equal to the square root of the other side, because we want to get V final by itself. So V initial, as given to us in the situation, is 0, and that's going to be plus 2 multiplied by our acceleration of 3.75 multiplied by your distance, which is the length of the ramp, which is 1.5. So when you put that together, get the square root of 2 times 3.75 is 1.5. You get a V final of 3.35 meters per second. So at the end of this acceleration, your object at the very bottom of the ramp will be traveling at a speed of 3.35 meters per second. So that's how you solve it if there is no friction. If there is friction, it gets a little complicated. So let's do the exact same problem, except our coefficient of friction will now be 0.2. So the same thing, but coefficient of friction will now be 0.2. So what that means in terms of problem is that a couple things stay the same and a couple things change. So we're doing the same values. So all of this is the same. Coefficient of friction is now 0.2. So what we have, same variables is what we're going to be looking for, net force, acceleration, and V final. Gravity does not change because that does not include a coefficient of friction. So therefore, FGY doesn't change and FGX does not change. Those things stay the same. What does change is that the net force in the x direction now includes friction. So F net x is no longer the same. So what do we know from the problem we just calculated? So we know, based on the previous calculations, that the force of gravity is 30 newtons, FGY is 27.82 newtons, force in normal is 27.82 newtons, FGX is 11.24. Okay, so now we still know the mass is 3, we know all the other piece of information, but as mentioned, the coefficient is 0.2. Okay, so how do we find the force of friction? Force of friction has one equation, technically two if you're using the net force to get the absence of it, but force of friction is the coefficient times the normal force. All right, and coefficient is 0.2. The normal force we already calculated, 27.82. So that means that our force of friction is going to be 5.564 newtons. And this is opposite the direction of motion, so it's technically negative x. So we have FGX and force of friction as our x direction forces. So we will calculate using our net equation. F net x is going to be FGX minus the force of friction because they're in opposite directions. So F net x is going to be 11.24 minus 5.564, which is 5.676 newtons, which is definitely less than the previous problem. Okay, so now that we know our net force, that's going to directly relate to what our acceleration is. So F net x, 5.676 newtons. And just like the last time, F net is equal to mass times acceleration. So this time we do 5.676 equal to our mass of 3 multiplied by our acceleration. So we are going to get 1.892 meters per second squared. We use the same kinematic equation to get our V final. So V final is going to equal the square root of V initial squared plus 2 times our acceleration times delta x, which is still the same. So we are going to get a V final of 2.38 meters per second. So in comparison, with the addition of this friction, our object at the bottom is going to experience 2.38 meters per second compared to 3.35 meters per second when there wasn't any friction. So it's about a meter slower when there's the friction. So when you're calculating it, that's what you have to take into account, is that now your net force is going to be not just FGX, it's going to be force of friction and FGX put together. So in general, you have a couple options. F net, like we have already discussed, is usually the sum of all your forces. So in the x direction, for the most part, you can have the force of the pull, you can have force of gravity in the x direction, and you're going to have force of friction. That's really it. So when you calculate and use your relationship, what that means is on occasion your problem will give you the acceleration, which means you know F net x. and they'll probably give you the mass, which means you know the force of gravity, which then sometimes means that you know the normal force, but sometimes not. And then once you know enough pieces of your equation, you can find force of friction sometimes by the absence of this equation. So what that means is that maybe you know mass times acceleration, and you know that the push is 100 newtons. And you know that friction is present, you just don't know how big, and you know based on the problem that your mass times acceleration, your net force is 25. Alright, so what that tells you is that your object is going to feel like there's only 25 newtons acting on it, when in reality there's 100 going one way and then an unknown amount going the other way. It's going to feel like there's 25, but there really is more than that. So when you do this, you're going to get the fact that the force of friction is going to be 75 newtons. So diagram-wise, you're going to have a force in one direction of 100 newtons, and you have a force in the other direction of 75 newtons, which ultimately is the same diagram as this, even though it doesn't look like it. These two situations are indiscernible unless you're told that there is friction and you know that you have to use this one. If you just know that the net force is 25, it makes sense that this would be what you're going for. Alright, so in general, that is your basic force lecture. It's very, 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 very minimal and very, very general. So I'm going to do a very slow scroll through the info here and talk about it again very quickly. So you have two different types of forces, contact forces and field forces. Your contact forces are anything that's in contact, so that would be push or pull, friction, normal force. Your field forces are anything that exists in a field, which would be force of gravity or magnetism. Now, normal force is a support force that comes from the surface, and the force of friction is dependent upon this normal force. So however much support or contact your object has with the surface is going to determine what the force of friction feels like. Now, depending on your diagram situation, on occasion your normal force is equal to gravity, sometimes it's not. So you always have to look at your free body diagram first to figure it out. Then you have, in general, the equation of F equals ma as your force equation. Your force of friction is coefficient times force normal, and your force of gravity is usually mass times gravity. All right, there are two examples of free body diagrams and a note that says that the normal force is always perpendicular to the surface. Then we know that normal force is equal to force of gravity, and if that's true, then your net force is 0, which means that your acceleration in the y direction is 0, your change in velocity is 0, which either means a constant velocity or a change in y of nothing. Now this is for the flat surface. And then you also are told that if force of pull is greater than force of friction, that means that your F net is not 0, which means that there is a non-zero acceleration, which leads to a non-zero change in velocity, which means that it is definitely changing position. So related to that, we didn't go over the ramp. Based on the ramp diagram, you have a y direction and an x direction. Now conventionally, I know we talked about this a couple times, conventionally your axes are set up like this, but on a ramp we change it. We just flip it sideways so that this is y and this is x, just so more things are able to cancel out. So for your F net y, the two forces that you have in the y direction are your force normal and your FGY. And they're in opposite directions. Alright, so based on this, since we already talked about this, I can draw it. Our ramp here is like that. So it's moving down to the right. Right. So we have F net y, which is force normal minus force gravity. So if those are 0, because it's not leaving the surface, that means that the normal force is equal to the force of gravity in the y direction. Then in the x direction, F net x is made up of all of your x forces, which in a situation like this would be FGX going down the ramp and force of friction acting up the ramp. So again, if these net forces cancel out to be 0, which is what happens if it's moving at a constant velocity, that means that Fgx is equal to the force of friction. All right. If this situation happens and they do not equal 0, then that means that either Fgx is greater than force of friction, which means that there is an acceleration, which means that there is a change in velocity, or force of friction is greater than Fgx, and that opens a whole other can of worms that we're just not going to talk about right now. Alright, so there's that. Okay, so we talked about that. Alright, in terms of equations, as I expressed to you, that we have systems, and systems are just the sum of forces in any given direction. So we have F net as mass times acceleration. That's also equal to the sum of your forces, which you can rearrange and ultimately get longer equations. So then, normal force, on occasion, is not equal to gravity. Sometimes it's equal to components, like we talked about, Fgy, but other times it can be a combination of Fgy or F pull y and force of gravity. So there are two situations. The normal force is lighter when you're pulling up, and it's greater when you're pushing down. So think like if you are leaning on a box and you're trying to push it across the floor, you're actually going to make it harder for yourself because you're pushing it down into the floor, not just sideways. And then if you're pulling up on something, you can usually make it a little easier because you're decreasing the contact, which is decreasing the friction. All right, and then here we have one sample problem with no friction. So we use that information to calculate the net force, the acceleration, and the final velocity. So all those are in boxes, so you can check that out. And then we have the same problem, so the same given information, looking for the same things, but friction is present. So in that case, we know that the net force is a little smaller because there's friction, so it's not moving as fast. So that means the acceleration is a little smaller, which means the V final is a little smaller. And then finally, I'm talking about the absence of forces. So on occasion, you will have a situation where you know the net force, and you know the push or the pull, and you're looking for force of friction without any other information. So the way that you do that is to use your net system, which says like 25 newtons is equal to 100 minus force of friction, and you solve. And then this diagram down here is just showing the difference between something with friction and something without. So this one is showing you that there is a normal force to the right, or a push force, I'm sorry, of 100 newtons, and there's a frictional force to the left of 75. And you can't tell if you were just told if there was a 25 newton force net, if the diagram on top is the diagram or the diagram on the bottom is the diagram, because both of them technically have a net force of 25 to the right. So you don't know officially which one is which. Alright, so that is your force stuff. If you have more questions, please let me know. But other than that, that covers the basics. Nothing too specific. I will do another set of videos for a couple different practice situations so that you can watch those as well. Alright, good luck.